Hello, Physics 11s. Today we are learning about uniform motion. You've already given your warm-up question a try, so let's go over it together. They give us the average velocity of the car, and they give us the time interval of this motion, and we are to determine the displacement of the car. So we will use the formula V average equals delta D over delta T. If we're looking for displacement, we can rearrange this equation by multiplying each side by delta t, and we'll have delta d equals V average times delta t. Go ahead and sub in your values, and we'll have 25.0 meters per second times 600 seconds. This gives us a displacement of 15,000 meters to the east. Our answer is supposed to be expressed to three significant figures. So this will be 1.50 times 10 to the 4 meters east. So what is uniform motion? Uniform motion is a term that we use to describe motion which is uniform in terms of its velocity. So uniform motion is where the motion of an object in terms of its velocity is constant. The velocity remains constant during that object's motion. So we can summarize this by saying V equals constant. You can also express this by saying delta V, or change in velocity, equals 0. So this means that the change in velocity is 0. In Physics 11, we'll be studying uniform linear motion, which means that objects are moving along a straight line. They're either moving north or south, east or west, left or right, up or down, etc. at a constant velocity. So we say that the line of motion is confined to a single dimension. Therefore, the displacement of the moving object will increase by the same amount for every second that passes. So this is a relationship of direct proportionality. We can say that the displacement is directly proportional to the change in time, or delta D is directly proportional to delta T. Since the velocity of the object is uniform or unchanging, the acceleration of that object must be 0. This is because acceleration is defined as the change in velocity per unit time. And if there is no change in velocity, then delta V is 0. So you get 0 over delta T, and 0 divided by any number is just 0. So this comes from there being no change in the velocity. So we can summarize that here by saying there is no change in velocity. Okay, let's do an example together. After crawling for 3 hours, a tiny ant has a displacement of 2.60 times 10 to the 2 meters to the right across the sidewalk. What is the average velocity of this ant? We know that delta t is 3.0 hours. Let's convert that into the SI units for time by multiplying by 3600 or multiplying by 60 twice. So this is 10,800 seconds of time. The displacement of the ant is 2.60 times 10 to the 2 meters. and we'll just say to the right here. We're supposed to find the average velocity of the ant, so we're looking for V average. As usual, we're going to solve by writing the formula, rearranging the formula, substituting known values with units, and then computing and rounding our answer to the correct number of significant figures. So let's start with our formula. Average velocity equals change in displacement over change in time. We don't have to do any algebra in terms of rearranging because V average is already isolated. So you can go ahead and sub in your displacement, 2.60 times 10 to the 2 meters divided by 10,800 seconds. Compute, and we get 0.024 meters per second to the right. Now our answer is supposed to be two significant figures because of the time given as 3.0 hours. This is two significant figures because this 0 is not significant. So you can leave it like this, or you can express your answer as 2.4 times 10 to the negative 2 meters per second right. That's your choice, either or. Okay, please try example 2 on your own or with the people seated next to you, and I'll check in with you in a few minutes. Okay, so in example 2, we're looking for the average speed and not the average velocity. Therefore, we're looking for how much ground the butterfly covers in the given time interval. Our formula is average speed equals distance traveled per unit time. We don't have to rearrange this, so we can sub in right away that the butterfly physically travels 5 entire meters, and it does so in 162 seconds. Compute, and we get 0.031 meters per second. We do not include a direction with our answer because speed is a scalar and not a vector quantity. Our answer should be expressed to two significant figures, and this is two significant figures, or you can express your answer as 3.1 times 10 to the negative 2 meters per second. These are both two significant figures. That's your choice. So for example 3, we're going to be doing several steps here involving calculating some data and graphing it. We're going to start by completing the data table. This data is from a mystery object moving at a constant velocity in the eastward direction. So to complete our data table, I'll get you started and then you can finish it off. We're given the time interval, the displacement of the mystery object. We need to calculate the displacement during the time interval and the average velocity during the time interval. We're then going to graph this column and this column on the same graph on the next page, and we're looking to identify the relationship between these two variables here. So to figure out the displacement during the given time interval, we're going to look at the difference between the total displacement, let's say at this stage, subtracted from the displacement at the previous stage. So in the first case, we have nothing to compare it to. So before we've gone anywhere, our displacement is still 0 and the average velocity during this time is 0 as well. But after 1 second is passed, the total displacement is 40 meters, so we can calculate the displacement during that time interval as 40 minus 0, and we will get 40 meters. Then our average velocity is the displacement in the time interval divided by the time, which is 40 meters divided by 1.0 seconds, and that gives us 40 meters per second during that time interval. I'll go through one more with you just so you feel good about it. Our next displacement during time interval is the difference between this stage and the previous stage. So it's 80 meters minus 40 meters, which gives us 40 meters in that time interval. How much time has passed between this interval and the previous? 1 second. So we have 40 meters divided by 1 second, which gives us an average velocity of 40 meters per second in that time interval. Okay, you keep going, finish your table, and then we can check our values together before you move on to the graphing stage. Okay, let's double check our values and make sure that we match. And moving on to the graphing stage. So it says here at the top, on the graph paper below, graph the displacement and the average velocity during time interval. These are the two shaded columns from the previous page. And it gives us some tips as well. We're going to label our graph properly with a title, axis titles, increment labels, and a line of best fit. So whenever I'm creating a graph to go with a data set, I always look and see what I need to fit on each axis. So we're graphing displacement and average velocity during time interval on the same graph, and each of them with respect to time. So our time axis, or our x-axis, has to go from 0 to 9. So it has to fit at least 0 to 9. So you can count this out. We can probably do it with a one-step increment. So if we had 1, 2, 3, 4, 5, 6, 7, 8, 9, that's really short. You always want to try and design your graph so that it is as large or spread out as possible instead of all small and squished into one section. So let's see if we can do a double increment for this. 1, 2, 3, 4, 5, 6, 7, 8, 9. That'll fit really nicely. So that means that we're going to start here with our origin. Grab a ruler to help you. Here's our time axis. We're measuring in seconds, and we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds. You can label each increment, but you don't have to. Commonly when we label our graphs, we can label at a standard set pacing. So I might label 2.0, 4.0, 6.0, 8.0, and then 10.0. And that allows you to map in or estimate your in-between values, and it's less cluttered along the x-axis. On the y-axis, we need to go from 0 to, well, we have to fit 350 for our displacement, and the highest average velocity value that we have is 50. So our graph has to fit 350. So let's take a look at what we can fit here. We might go to 400 on this axis. We could go 50, 100, 150, 200, 250, 300. Actually, that'll work, 350. So let's do a double increment jump is 50, 100, 150, 200, 250, 300, and 350. Okay, so we're going to plot each data point. We start at the origin, and then we have 40 meters of displacement that occurs after 1 second. So here's going to be our displacement value. This will be 25 right here, so just estimate your 40. It's not a big deal because we're going to draw a line of best fit. And then we're at 80 meters after 2 seconds. So that'll be 75. At 3 seconds, we're at 130. And keep going on your own. So when we draw the line of best fit, our goal is to try and put the line through as many values as possible, and if it's not going to go directly through those values, it should have them balanced on either side of the line. So we wouldn't want to draw a line here because we end up with too many values above the line, and likewise we wouldn't want to draw our line here because then we have too many values below the line. So just try and estimate to the best of your ability where that line should fall. I'm going to draw mine like this. So this is our displacement measured in meters. When you're finished your displacement line, you can go ahead and do your average velocity line. Our values range from 0 to 50. What we'll do to reduce experimental, or well, since this is experimental data, to reduce the error that came from this, we're going to eliminate the first velocity value that came from calculation, and as you'll see, all these values are around in the same range. So we're going to leave this one out because we're assuming that the average velocity was 0 during that time interval. It hadn't started yet. Obviously the mystery object is accelerating during this range, and it's okay to leave that out, and I'll talk more about that later. So start with your first data point at 40 meters per second. I did my data points with X's just because we have two different data sets plotted on the same graph to help us tell the difference. So I'm going to go ahead and draw my line of best fit here for the velocity data. I think about here is reasonable. So this is our velocity measured in meters per second, and maybe I'll label that V average. Once you're finished your graph, please spend a few minutes thinking about what is the relationship between these two quantities. How is displacement related to average velocity? You can pause the video here while you give it a try, and then I will chat about it in a moment. So what I'm hoping you observed is that displacement and average velocity are related to one another. If you look at your data for the displacement and you compare the slope of this line to the value of your average velocity, you'll see that they are very closely related. So just a reminder that the slope is defined as the rise over the run of a line, and here the rise that we experience in our data for the displacement is about 350 minus 0. So again, we're going for our minimum y value to our maximum y value. So final minus initial, 350 minus 0, and the run that this change takes place over is 9 seconds minus 0 seconds. If you calculate this, you get 38.8 repeating meters per second. Those are the units because we had meters in the numerator and seconds in the denominator. So this is approximately, let's just call it 39 meters per second, which is roughly what our average velocity line of best fit shows as well. If this is 50, where maybe my line's a little bit higher than it should be, but if that's 25 and that's 50, then we're pretty close. We're somewhere around 40 meters per second. So let's summarize this relationship. The slope of the displacement versus time graph gives the velocity versus time graph. This is a situation of uniform motion, so we would expect our displacement to be changing at a constant rate, producing a constant velocity, because velocity is the rate of change of displacement with respect to time. This graphical relationship is not intuitive. We will be spending more time with it during our next lesson, but for now, please continue to assignment 3. Make sure to check your solutions when you're finished, and I look forward to seeing you soon. Have a great day.